Welcome. So we'll be graphing log functions in this podcast. So our next function to graph is g of x equals log base 2 of x. All right, so first of all, let's just look at this part, this base here. And maybe we can, there we go. All right, and so we're going to rewrite that into exponential form, and we're going to ignore the 3 for a moment. All right, so in exponential form, that would be 2 to the y equals x, right? Because base raised to a power, so log is just an exponent. When you evaluate a log, you're just saying, what's the exponent I got to raise this base to get this result? So base raised to a power gives us some result. All right, so we're going to plug into y and solve for x. I'm going to plug in -2, -1, 0, 1, 2, and 3, because this grows a little on the slower side. So we have 2 to the -2. That would be the reciprocal 1/2 squared, or 1/4. 2 to the -1 is just the reciprocal. 2 to the 0 is just 1. 2 to the first is 2. Oops. Missing part of my 2. 2 squared is 4, and 2 cubed is 8. Now, I'm not going to graph that right yet, because now I'm going to deal with the 3. All right, so now, remember we said that a log is just an exponent. Well, using the power rule, actually, I'll put it right up here, since I'm talking about that 3, oh, right below that, so I need to orient a little bit. All right, so the power rule here, let's see if I can move that up a little bit. There we go. Says that I can rewrite 3 log base 2 of x. This can go back and be log base 2 of x cubed. Now, you wouldn't want to solve it like this, because actually it's a little harder. Actually, it's a lot harder. There's a much easier way. But the reason it can do that is that coefficient can move back up there is because it's an exponent, right? Power rule says that since the log's an exponent, that if I have an exponent on my term, I can move it in front, because what do we do when we raise power to a power? Because the x is raised to a power, right? And that log base 2 of x is just an exponent. When we raise power to a power, we multiply exponents. So the exponent can become a coefficient. Right? And so this is an exponent, and log base 2 of x is an exponent. And when we raise power to a power, we just multiply the exponents, which means we can multiply the 3 and the y value, because the answer is the exponent, and y is the answer. When we take a log, we're getting the answer is the exponent. So rather than rewrite this as log base 2 of x cubed, and then have to solve 2 to the y equals x cubed, and do a whole lot more work, we could simply do this. We can just get 3y, right? Because the y's are the exponent and the 3 is the exponent. So that's going to make this -6, -3, 0, 3, 6, 9. All right, so now we can just graph the 1 graph. Let's graph our vertical asymptote first, and then we'll graph our function. So the vertical asymptote is x equals 0. This was not shifted in any way. Right? And right and left is the only thing that is going to change your asymptote. And then we'll graph the points. Be careful, make sure you look at the right columns. It's easy to look at the wrong column and like look at the y and the 3y. That would not be the right thing to graph. You want to graph 1/4 -6 and half -3 and 1 0 and 2 3 and 4, 6, see, it's easy to grab the wrong one, and 8, 9. All right, and it's just going to fit underneath my red writing there. Maybe I should graph it in blue, all right, because it's going to go right into probably the red writing there. So we have 1/4 -6, 2, 3, 4, 5, 6 right there. Oh, by the way, this one is in the notes. 1/2 -3, 1, 0, 2, 3, and 4, 6. And then 8, 9, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, right into the writing. That's okay. I'll stand out there. There we go. And of course, it would just keep going. And you could still see the writing. And I could always move it around a little bit later on. Right? And so here you can see the function is growing much faster because we're not doing anything to the x, but we're tripling the y's. Right? Domain unchanged at 0 to infinity. And range is always -infinity to infinity for log functions. And there's one down. Right? So let's look at this. So this one is very, very similar to this one. This one reflected it, made all the y's negative. This one made them 3 times as much. And that's what you'll always do with a coefficient. If we had a coefficient in a transformation, we do the coefficient first. We'd multiply the y's by 3, then we do the transformation. This is just one graph on this one. You can do this in one graph, so long as you write down your points. You triple your y's. All right, so here we have a little bit different one. All right, so now this time, there's no way to get the 2 out of there. The 2 is stuck in there because it's not the log of x times something. It's the log of 2x. All right, so we'll just rewrite it. This is going to be no big deal. All right, so base raised to a power gives us an answer. We'll just have to solve for the answer, but it's so easy to solve. You just got to divide by 2 once you set it up. So exponential form, I probably should write exponential form instead of just writing the equation, so you know and you're reminded this is exponential form. So back here, this one was, well, I kind of did exponential form. All right, so this one is going to be 4 to the y equals, instead of x, it's 2x. No biggie, right? All right, so, I'm gonna run out of x's long before I get very far on the y's. So I'm gonna use -1, 0, and 1. So I tried to use 2. Actually, on this one I can, because it's 2x. This one I can. And yeah, we're fine, I think, with just the negative. Well, we'll plug in -2. What the heck? Let's plug in 5 points for this one. I think we can graph this one. All right, so now it's going to be 4 to the -2 doesn't equal x, it equals 2x. Oh, actually, what was I thinking? We're never going to get that one on there. The other ones, yes. If I divide them in half, it's going to make them smaller. But I forgot. If I divide it in half, it's going to make it smaller. Well, we can write it down. And it's going to be super small, well, kind of small. So, because 4 to the -2 is 1 over 16 equals 2x. And if I divide that by 2, right, it's the same as multiplying by a half. I have 1/32. I should have been thinking there. Hey, it's getting smaller. You don't want the negative so much. That's all right. We're not committed to graphing it. All right, so this one took up all that space too. All right, but the next one we'll graph. 4 to the -1 equals 2x. So if 1/4 equals 2x, we divide by 2 or multiply by a half. All right, x is going to be 1/8. We'll graph that one. We'll just forget all about the -2. Sorry, we can do that. You can choose a value and say, well, I think I'll leave that one out because it's really hard to fit on the graph, or it's so teeny tiny. It's hard to divide one space into 32 pieces. All right, so then 4 to the 0 equals 2x. This is just 1 equals 2x, so x is 1/2. All right, so notice all these values are just half as much as you thought they would be. or they would normally be if this was just a 4x. Let's see if we can squeeze the last 2 in here. So 4 that I would have been able to if I didn't choose -1, -2. So 4 to the 1, 4 to the 1, 4 to the first equals 2x. That's just 4. If I divide by 2, 2 equals x. We'll save a little bit of space here. 4 squared equals 2x is the last one. Maybe I should put some lines here, just kind of help you see where each one goes. And in terms of the table of values, write in as much as you think you need. All right, and so this would be 16. So 16 divided by 2 is x, so x is 8. Let's see if I can just move things up just a wee bit. There we go. No, not turn them around in a circle. Well, okay, there's that. Let's see if we can unrotate. There we go. Turning around in a circle was not my goal. 8 equals x. There we go. So we will skip the first value. All right, 1/8 -1 is really just small enough. I mean, I can't, and that's not even really at an eighth, is it? Because my dot takes up too much space. It's not 0, but it's so close. So close. All right. Oh, and speaking of so close, our vertical asymptote is x equals 0 because we didn't shift. We did not shift horizontally. Therefore, it remains at 0. All right. So this is just going to be a base graph. All right. So we have 1/8 -1. We have 1/2 0. So you notice the x's are just growing twice as slow. Half as much. I think that sounds better than twice as slow. Half as much. And then 2, 1. That's what enables me to be able to put 2 on there, because normally I can only get 1, because normally 2 would be all the way at 16, but I can get 8 in this graph. And then what are we missing? We're missing 8, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 2. There we go. And all of our log functions grow much, except for if we have a coefficient in front anyway. They grow much faster on the x's than they do on the y's. This was not shifted, right or left. Therefore, 0 to infinity is the domain. The range, as always, all real numbers, -infinity to infinity. All right. I'm only going to do a little bit more. That was the end of my log functions. Showed you all the different things we could have. Right? And so this is going to be a whiteboard practice in class. And we're going to look at the very beginning of one more log function, and it's just a different base. So because the functions given by f of x equals e of x and g of x equals natural log of x are inverse functions of each other, their graphs are reflections of each other in the line y equals x. Right? So now they're inverses as well. Right? So an exponential in a base and a log in the same base, they are inverses of one another. Their graphs will be reflections over the line y equals x, and this is in your notes. All right? And of course, if you ever need to evaluate natural log, you have it in the calculator, and it's denoted by ln. And usually e to the x is right above it, and you just have to hit shift. Or second, depending on your calculators. So we're going to graph natural log of x, and then we're going to graph, that's our base function, we're going to graph natural log of x minus 3. And how do we graph natural log of x? Of course, we rewrite that in exponential form, just like we've done all the other graphs. Right? So here, of course, this is just y, right? The g of x is the same as y, just in function notation. So our base is understood to be e, right? When we see natural log, base is e. Right? So instead of our base being written, we just have to remember the base is e. So e to the y equals x. That's all there is to rewriting this into exponential form. And we spent time doing this at the beginning of this whole unit. So we're just going to plug into y and solve for x. Right? And if you remember graphing e to the x, you can remember some of those the values there and what would fit. I'm going to put -2, -1, 0. You don't remember exactly. You kind of remember how much they were, and 2. No point in going any farther than that. All right. So, and often you might want a calculator. I believe it's 0.36 for e to the -2, but don't want to totally rely on my memory. So let me just plug this in the random calculator I was able to reach. And no, about 0.36. That's e to the negative 1. 0.135. So see, it's good. They didn't. 0.135. When I'm graphing these, they're stuck in my head. And if I haven't graphed them in a little while, other than e to the first and e to the second, of course, this one here, e to the first, is going to be 2.71. And of course, e to the 0 is going to be 1. And I think e to the negative 1, that was the 3.6. So, but let's double check that. And so I'll just plug that into the calculator. That one was 3.67. 0.367, excuse me. And then e squared is about 7.4. Let me get the other decimal there. So e squared is, well, 7.4, but if I want 3 decimals, it's 7.39. All right, so there we go. Not that we can graph any more accurately than 7.4, but I'll put 3 decimals for those ones. Or, I mean 2 decimals for those. All right, so let's graph that. All right, so we have negative 2, 1.35 negative 2. All right, so that's about a tenth, a little bit more than a tenth. Halfway between a tenth and a fifth, really, just about. And then on negative 2, so about there, I guess. Good enough. And then, of course, we have that's about a third at negative 1, so about there. I should make my dots smaller. And then 1. And then we have, oops. Yeah, there's my value. We have 2.71. I looked too quickly. So I keep reading these backwards because I'm standing to the, so it's on my right hand, my left hand side. So I keep wanting to read it the reverse direction. 2.711 is that number there, almost at 3, not quite. And then we have 7.392. 1, 2, 3, 4, 5, 6, 7 and a third. And 2, and there it goes. This graph, the natural log will grow a little faster than 2, not as fast as 3. Let me move that down just a wee bit, just a little higher. There we go. And we do not want to cross the next line because I would not get to the next number, would not get to 3 until x was 20, a little bit more than 20, 20.09 to be exact, or approximately. And so that's not going to fit on this graph. I'll be on the board somewhere. You won't even see it. All right, so there we go. Our vertical asymptote is x equals 0. Oh, excuse me, we have to do we have to shift. Well, it would be x equals 0 if we weren't shifting. We're shifting 3 to the right. We want to graph this one. All right, so our vertical asymptote is going to be x equals 3, and it's already graphed there for us. All we have to do is move those points over 3 spaces. No biggie. Don't even need to count, right? You can see what 3 looks like. Oh, and this is in your notes. And there we go. So because we shifted to the right, our domain has changed to 3 to infinity, but the range, it never changes. There we go. And another one done. All right, so here we have g of x equals natural log x plus 2. Maybe this will be the last one we do. I have 1, I have 2, I have 3, and something happened to this one. 4, I'll write the rest of that one in there. I only have 4 more to go. So let's call the one we just did the last one, and I'll do the last 4 in class. All right, thanks for watching the podcast, and there'll be a couple questions for you to answer, and then we'll take a look at the last 4 graphs and a little bit of exponential graphs. All right, bye for now.